I think in my head I do like 52 or something. Sorry, 3.5 hours of sleep. But now I have 72 microcoulombs of charge on this. And then if we boil this all the way down, what we did was we basically said this, right? We added everything up and said this is 4 microfarads. Right? What do we do? This is called a what? Condensation, right? This is condensing. It's 18 volts. So what that means, so this means there is 72 microcoulombs of charge there and minus 72 microcoulombs of charge there. Does that make sense? Well, what does that break down into? What is connected directly to the positive side of the battery? This. And please notice where I'm putting these lines. Here, 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 and there. Do you see that? What is connected directly to the battery? Only those 4 capacitors. And then this 72 coulombs has to be spread out over those 4 capacitors. Well, technically, over these 2, and then another 72 over these 2. All right? So if I go and look at this, these 2 are both the same. So is there any, like, reason to put more on one than another? No. So that means 36 microcoulombs here, 36 microcoulombs there. So these are both plus. Now, over here, this, what is that capacitance? I don't think so. It's 3. I mean, for some reason you want it to be 18, but it's only 3. Right? This is 3. If I put it with that, I'm going to mess it up. So what I'll do is I'll write that in blue and say this is 3 microfarads, right? Just this side is 3. And this side is 6. So that means the 6 must have twice as much as the other side. Okay? So that means this one must be 24 microcoulombs, and this one must be 48 microcoulombs. And that's going to be negative. Yes, because they're both connected to which end of the battery? So what charge would they get? They would get the negative charge.
So then you only have later post.
No, it's just once that's done, I know this is negative 36. This is negative 36. This right here is positive 24. That's negative 24. This is positive 24. And then this one is negative 48. Or sorry, positive 48. Right? And then now there must be 72 on here. It's divided by 3, so this is 20, positive 24, positive 24, positive 24, negative 24, negative 24, negative 24. So thanks for asking. See, at each juncture, there must be a total of like 72 on those capacitors. So it's kind of like 3 groups of things, right? This one, that one, and this one. To be honest, on a test, you're not going to get one this difficult. But it's like I'm trying to make you do something harder so that you can be ready for something. Well, at least I think so. I'll tell you something. Yeah. Actually, I won't tell you.
So you will you turn off when you put the negative?
Yeah, because you can't have positive on both sides. Okay, questions on that? All right, that's the first half. And so we move on. Okay, this one, if you didn't get this, you should be beaten about the recent with a large metallic impact.
Yay.
Just kidding, by the way. You do not deserve to be beaten in any respect. Obviously, you didn't have to do that in multiple colors, but that's the idea.
Oh.
Oh, okay. It's there. So this is an example of the positive and the negative with the electric field looking like this. So you just have to show some sort of like bending towards from this to that. Does that make sense? Questions? Alrighty. So then, oops. Move on to here, to the second part, which says if two charges have that magnitude, what would be the force between them? Whose law do we use? Coulomb's law. So F sub E, the force of the electric field, or the force of the electric attraction, is K Q1 Q2 over R squared. So it's going to be 9 times 10 to the 9th newtons meters squared per coulomb squared. And then I'm just going to go 500 times 10 to the minus 6 coulombs squared over 1 squared. Because it's micro. That means minus 6. All right? So then, hello.
We're here for one.
Can I take Raymond out to help out for like 10 minutes? Or I want to go.
Oh,
Yeah, Raymond.
yeah.
Okay. Hang on a plastic.
There's one. Okay, so does this part make sense? I'm just plugging it in. This is K, that's Q1, that's Q2, and this is R. So then I can do certain things, right? Like I can say, this is actually 5 times 10 to the minus 4. If I square that, I get 25 times 10 to the minus 8. So then that's going to give me 9, like 90 times 25 over 1. And so then 9 times 25 is like 220, so it's like 2250 meters per coulomb.
Wait, is that negative 6?
Yeah. Yeah.
Why is it squared?
Because Q1 and Q2.
Have a nice weekend, Mr.
Oh, okay, so then.
What's that?
Have a nice
Oh, yeah, you too, buddy. Remember, let me know when that video goes up. I want to see my dad's jacket in action. Okay. Questions on this? It's just plug it into the formula. Oh, wait, sorry, just kidding. It's not newtons per coulomb, it's newtons.
Is it old?
Is that a 1 on the bottom?
Yeah, it's just newtons.
It was, I didn't know you have like, it's like 10 to the minus 6, so I got 2.25 times 10 to the 15.
Awesome.
And I was like,
That's a lot of force.
Yeah, when you were talking about the other one in, like, in our notes, it was like a lot less, it was like 1 point something newtons.
Yeah.
Oh.
Okay, so we good with this?
Or is it 500 times
500 times 10 to the minus 6, because that's microcoulomb.
1? Oh.
Okay? So we clear that. We can move on. So this says,
Can you, like, come on this side? Can you stop pushing?
okay, so this one says, if you were directly in the middle, what would be the electric field strength and electric potential? So if I go minus like that, and I go plus like this, and we're looking for this spot right there. Okay, so what is the electric field strength first? What is the equation for electric field strength? KQ over R squared. Now, what is the blue one going to do? What is the negative one going to do at this point? Show me a negative electric field. Go. Right? So if I put my hand like this, you see my fingers are supposed to be pointing that way. Does that make sense? Okay, what does a positive do? So, what is the red one going to do at this point? Right? It's like a field, so that when you're a certain distance away, you can still be affected. It's kind of like smell or stink. You can tell somebody hasn't bathed even when you're not next to them. Right? And the farther you're away, the less the effect. Now, these two both have the same magnitude and the same distance, so the effect is pretty straightforward. In fact, I can just multiply this by 2. Does that make sense?
No,
Why
why?
They both, because we have to add up both of these red and blue ones. Does that make sense? Yes? and then they're both the same size because they're both the same magnitude and they're the same distance.
Wow.
I mean, okay, so what I could do is I could do like this. This is the first one. This is the second one. What is true about K? Same. What's true about Q? Magnitude of Q? Same. What's true about R? Same. So it's just 2K Q squared over, oh, I'm sorry, not Q squared.
I was like, what?
Q over R squared, which is 2 times that. So then I plug that in, I get 9 times 10 to the 9th times 5, let's say 5 times 10 to the minus 4 times 2 over 0.5 squared. Okay, so this becomes 10 times 10 to the minus 4, or 1 times 10 to the minus 3, which makes this 9 times 10 to the minus 6. That's 0.25. That divided by that gives me 36 times 10 to the 6th.
Wait, why
Newtons
5
per
times 10
coulomb.
to the
Yeah, why?
Because you know how he did 500, just change it to this stuff.
I turned it, instead of 500 times 10 to the minus 6, I did 5 times 10 to the minus 4.
Why?
Because that's the power of, you don't know the power of scientific notation. Anyways, by using the scientific notation, you can get a thing where you're multiplying the beginning number easily. Do you get it? I'm doing 9 times 5. And then I just take these and put them together. That's the cool thing about scientific notation. You can break the power away from the digit and then turn it into single digit multiplication and then add up the exponent. It's just a way to do it faster, whatever. And then I'll do this in red. V is K times Q1 over R1 plus Q2 over R2.
What? Oh, you don't do the Q1 to Q2 over R?
No, because it's electric potential. Electric potential is V. Okay? Now, so this becomes 0. Because this one doesn't have absolute values. Yeah.
Did it just say R
Yeah, it said they're 50 centimeters from the charge, so these are both the same R. No, if you were in the middle, yeah, it adds up to 1, but we're not concerned about plus and minus, we're concerned about plus. Oh, here to here, we're concerned about there to there.
So I didn't find out
Yeah.
two different times.
It's not a. We're not asking how the plus affect minus. We're asking how do plus and minus affect that. See, so it's not like we're not asking how you and I are interacting. We're asking how we're both interacting.
Because then, like, after 2 meters.
Oh wait, no. Never mind.
But maybe 1 to 6, so it'll be 5 millimeters.
Yeah, number 6, we're asking about plus and minus.
But you won't be able
You see, we're asking plus and minus. So 1 meter. All right, questions on this?
Just one more time with the 10 to the negative 4.
Yeah, so it's 500 times 10 to the minus 6. Okay, so that is 5 times 100 times 10 to the minus 6. What's 100 times 10 to the minus 6? That's 10 to the minus 4. Yeah, you move the decimal. Does that make sense? Questions? Any other questions? I'm telling you, scientific notation. It's incredible.
And all this is on your block line.
Yep, actually, this is going to be on there and the other one. So this part will at least be customized for you guys. All right, so then here we have this, and then up here we have this. Same distance, everything. So the issue is, what is the mass of this floating positive? Well, what two forces are affecting the floating positive? Gravity and the electric force, right? The attraction. Okay, don't be an idiot. Do we know this? Yeah, we found it out in 6. So I just say Fe equals Fg, so it's going to be 2250 equals mg. M is 2250 newtons divided by g, so it's around 225 kilograms. And that is a big ass floating sphere. And I recorded. Awesome. All right, so just be aware that for FE, make sure that you're ready to use Coulomb's law completely. All right. Also, make sure that you could do something, because I could do something really sneaky like this.
Don't do that.
Like the other one.
Nuh-uh. Don't do that.
So you could see that too, because we just did that the other day.
No.
I did.
It hurts.
So all who are watching this, make sure you know how to do this one too.
Okay,
I'm dying.
Want to do that one again on the board?
No.
Yeah, we can knock it out. It's just boom, boom, boom. Here, here, t cos theta, t sine theta, fe, fg. So we get t cos theta equals mg, t sine theta equals fe, which equals eq, because I wanted the electric field. So then we get mg over cos theta equals, because I solved both for t, eq over sine theta. So then E is going to equal mg over q tan theta.
Where'd you get
Because remember the electric field strength was F over Q.
Oh.
So then F is EQ.
Wait a minute.
Yeah.
Why is FE pointing this way?
Why is FE pointing that way? Because if this is hanging like this, make this look like that. Yeah, see which way did you push?
Wait a minute. Why are you
That's what I told you. When we did that problem, I said find E.
There's no
Oh,
number.
what's this?
Yeah, and this there's no numbers.
If you say G, if you say 510,
Yeah, exactly. Did you hear Connie's question? What if you're supposed to find M? Well, then just solve for M. No worries. In that case, I would have to give you the E.
that's on the string, right?
What's that?
That's on the string. That's
That's, sorry?
the little thing on the string.
Oh, yeah. That was on the string.
What little confidence I did have. I'm gonna look.
Alrighty. I will say